Okay, we're going to take a look at chapter 5, which is compounds. We're going to take a look at compounds in a couple of different forms. Mostly right now, we're going to be looking at ionic compounds. So, and we'll explain what ions are in a little bit. But before we start, last chapter, we talked about electron configurations. And we did these really long electron configurations. And again, we noticed that they always were the same until we got to a noble gas. The last line was slightly different, although it filled up how we would expect it to. So if we write the condensed configuration for all of these, what do we get? So right off the bat, let's pause this and write out the condensed electron configuration for every single element here, okay? So I'm going to pause this and write out at least one of each group, group 1 all the way out to group 18. Okay, so here are all of the electron configurations for every single one of these. Normally in class, I would divide it up and have everyone do one, but it's good practice to be able to know these things. So if we look through this, let's take a look at group 1. The noble gas core, which we know is incredibly stable, and we're going to talk about that a bunch. 2s1 for lithium, 3s1 for sodium, and potassium is 4s1. So it is always the noble gas core and ns1. So the really important thing here is the s1 part. So it is n, it is, row 4, row 5, period 4, period 5. But really the thing that we're focusing on is the fact that it is s1. Okay, so s1 electrons. Okay, group 2 is going to be some amount, same exact idea, ns2. ns2. Okay, and on we go. So group 13, group 14 is ns2, np1. Again, you'll notice that every single one of those has that same configuration. Group 14, ns2, np2, or s2p2, okay? The next one, ns2, np3, ns2, np4. Again, every single one of these is the exact same. np5, and then finally the noble gases are always ns2, np6. The important part here is that we are talking about the electron configuration, or I should say s2p6, that has 8 electrons. This has 7. This has 6, 5, 4, 3. Those line up with the group numbers. So group 1, group 2, group 3, group 4, group 5, 6, 7, and 8. Okay, so the number of valence electrons, the number of these electrons that are outside the valence. So essentially you have the noble gas, and anything beyond the noble gas core is what we call valence electrons. So valence electrons are the outermost electrons in an atom or ion. Okay, we'll talk about ions as well. What we are going to notice is, of all of these groups on the periodic table, the noble gases are the most stable. Okay, they don't react. Helium, argon, neon, none of these things react. They prefer to just be a gas by themselves with nothing else. And the reason that they do this is because they have 8 electrons. We often call that an octet. An octet is a super stable configuration. Every single one of these atoms wants to achieve a stable configuration in the form of an octet. So atoms will add or remove electrons. And so here we're going to get into the idea of how we form these compounds. But atoms will add or remove electrons until they have the noble gas configurations. So 8 electrons is stable. That's what we're shooting for. 8 electrons is stable. All things want 8 electrons. That's always what we're trying to achieve. Okay, so every single one of these is going to have a certain valence shell and a certain number of electrons, but they're always going to want to try to achieve 8 electrons. So the number of valence electrons, okay, that V stands for valence. Group 1 has 1 valence electron, group 2 has 2, group 13 has 3, 4, 5, 6, 7, and 8 valence electrons for group 8. Okay. There's a couple of ways people represent this. Okay, so if I had, let's say, sodium, it has 1 valence electron. You usually use dots to represent electrons. Let's move down a little bit. Boron has 1, 2, 3 valence electrons. Let's move down even further to, let's say, carbon, 1, 2, 3, 4. It's in group 4, 4 valence electrons. If we check out nitrogen, 1, 2, 3, 4, and we're going to start pairing them up. So there are 5 valence electrons. We call these Lewis dot structures, but we're going to talk about that a little bit later. And again, all of these are the just representations of how many valence electrons we have. 1 valence electron, 3 valence electrons, 4 valence electrons, and again, this has 5 valence electrons, and we can take a look, and we always know based on the group number. Sodium's in group 1, boron's in group 13 or group 3, so on and so forth. Everything will always try to achieve 8 electrons. Okay, so when we look at these things, we know that they have a certain number of valence electrons, and what they're going to want to do is they're going to want to add or remove electrons in order to be stable. So let's take a look at sodium. Okay, so sodium has a configuration of neon. It has NS1, neon NS1, or just simply 1 valence electron. Ultimately, we don't really care about the neon portion of it. We just care about how many valence electrons it's got. So sodium has 1 valence electron. So when sodium becomes an ion, and an ion is a charged atom, and it becomes charged by adding or removing electrons. Okay, so sodium is going to gain or going to lose electrons, and ultimately it wants to get to an octet. So sodium has 1 valence electron. It has a choice. Sodium can either lose 1 electron, right? And it's going to end up, if it loses that 1 electron, and this is I'm going to do it this fancy way or just this long way with just this one. So sodium again has a choice. If sodium loses 1 electron, right? So sodium being neon, let's see, 3s1. If it loses that 1 electron, it now is just going to be a neon core. That's it. But more importantly, if it loses that 1 electron, I'm positive I lost an electron. It becomes +1, and now it has a noble gas core of neon. Okay, so essentially it's gone from 1 valence electron to 0 valence electrons, but what it's really done, it's gone from neon with 1 electron to just neon. Again, we're looking for stability, and that's stable. The other choice for it is to gain 7 electrons. Okay, so I have a choice. If I'm going to take the number of valence electrons, and am I going to lose them all, or I'm going to gain them to get to 8? Okay, and when this sodium gains 7 electrons, it would become, well, it gains 7, so 7 minus. It's going to be neon and 3s2, 3p6, because it gains 6 more. And this, of course, is just simply argon. So either way, it would have ended up as a noble gas. So the ultimate question is, which one of these is most likely to happen? Lose 1 or to gain 7? And you would guess it, the lose 1 is what's going to happen. It's much easier to get rid of 1 than to gain 7. Okay, and it's going to be just that simple. Okay, so sodium gets rid of one electron and it likes to become sodium plus one. Let's take a look at oxygen. Now we're going to simplify it a little bit. Remember, we want oxygen is going to have 6 valence electrons, okay? So with its 6 valence electrons, it has a choice. It is either going to lose 6 electrons to become O6 plus, or it is going to gain 2 electrons to become O2 minus. Again, losing 6 brings me to 0. Gaining 2 brings me, because I started with 6 valence electrons. So starting with 6, losing 6 gives me to 0. Gaining 2 brings me to 8. Either way, that's a noble gas, and that's the stability we're going after. So either we're losing them all, or we're adding until we get to 8. So we have a choice. Easier to gain 6, or to lose 6, or to gain 2. And the answer is, it's easier to gain 2. Oxygen tends to form O2 minus, okay? So with that said, what do we expect for gallium? What do we expect for bromine? What do we expect for krypton? Okay, so take a moment. Well, I'm going to do these right now. So take a moment, pause this, and decide what ion do you expect gallium to become, right? Is it going to gain? Is it going to lose? Same thing with bromine. Is it going to gain, going to lose, and krypton? Okay, so just pause this, and I'm going to take a look at it right now. So how many valence electrons does gallium have? Gallium has 3 valence electrons. So it has a choice. Gallium can either lose 3 or it can gain 5. Which do you think is easier to do? Gaining 3, it's a smaller number. Gallium 3 plus, that is what we are going to end up with, gallium 3 plus. How about bromine? Same question. Bromine is in group 7, so it has 7 valence electrons. Easier to lose 7 or to gain 1. Gain 1, bromine minus, you should end up with Br minus. Okay. How about krypton? So we know that krypton has 8 valence electrons. Easier to lose 8 or gain 0. Okay, because it doesn't need any, because it already is full. Krypton will not form an ion. It doesn't prefer to do that because it already has that noble gas core. Okay, so that is the preference. Nothing is going to change. And we can do that across, and we're going to see some trends here. Okay, so now that we have this, look at every single one of these on the periodic table and just take 1 or 2 from each group and decide what do you expect to happen for every single one of these. Okay, so I'm going to pause it while you work through that. Okay, so anything in group 1 has 1 valence electron, and therefore it's going to have a preference. Either is it going to gain 1, is it going to gain 7 or lose 1? And all of these are going to lose 1 electron. So hydrogen becomes +1. Lithium, +1. All of these in group 1 are going to become a +1 charge. Everything in group 1 becomes a +1 ion, okay, because it wants to lose 1. Group 2, easier to lose 2 or to gain 6. It's easier to lose 2. So everything in group 2 becomes 2 plus or +2. Everything in group 2 forms an ion of +2. Okay, let's go all the way to the other end of the periodic table, and you're going to see why in a bit. So group 18, 8 valence electrons. These do not form ions. They are happy being just neutral, right? Every single one of these is just going to be neutral. No ions are formed of any type. They're happy to be what they are. How about group 17? Okay, group 17 has 7 valence electrons. Easier to lose 7 or gain 1. Easier to gain 1. Every single one of these is going to have a -1 charge. Okay, so -1. Group 16, easier to lose 6 or gain 2 to get to 8. Everything here is going to be 2 minus. How about group 15? Easier to lose 5 or gain 3. These are all going to gain 3, 3 minus. Phosphorus 3 minus, arsenic 3 minus. How about group 13? Group 13, easier to lose 3 or gain 3. Lose 3 or gain 5. It's easier to lose 3 plus 3. Okay. So 3 plus, aluminum 3 plus, gallium 3 plus. And now we get to carbon. Carbon, lose 4 or gain 4. Well, we're not really sure. It could go either way. So these tend to not like to form ions either. Carbon and silicon actually like to form a different type of bond. So typically, as you are out near the edges, these are group 1 and group 18, or sorry, group 1 and group 17 love to form ions, and they'll always form those charged ions that they have, right? So group 1 always +1, group 2 always +2. Yeah, so always. Group 17, most or pretty much always, mostly -2. As you get closer and closer to the staircase, things tend to change a little bit. Boron, these pretty much are always as well, but I'm going to say mostly because we have some indium and thallium and some other things. And that's it. The point being is the ends are absolutely certain, +1, -1, +2, absolutely. Oxygen -2 pretty much all the time. But as we get closer and closer to carbon, the ions are less and less certain. And there's another thing that we want to take away from this is all of the metals form positive ions. And all of the nonmetals up here in this corner form negative ions. They like to gain electrons instead of losing them. Okay, so that is typically what we see. We have to recognize the important information to take away from this. Group 1's +1, group 2's +2, -1, -2, and we can determine that these are +3 and -3, but as we get closer and closer to carbon, we become less and less certain. So that brings us to actually the first section here was talking about ionic compounds. So now we know how ions form and whether they like to form positive or negative ions. The compounds that we're going to look at come in 2 main forms. An ionic compound is going to contain 2 ions. So if I have sodium, the one we know really well, with 1 electron, in chlorine with 7 electrons because it's in group 17, these are the neutral versions. So when I bring sodium and chloride together, sodium is going to have a choice: get rid of 1 electron or gain 7. Chlorine or sodium is going to be happy to just get rid of that electron and actually just give that electron over to chlorine. And so when that happens, sodium, now having lost an electron, becomes a +1 charge. Chlorine, having gained that electron, now has a -1 charge. Okay, so now that it has gained that electron from sodium. Okay, and in fact, I can just highlight it. This green electron here is now this green electron here. So it belongs to chlorine. I just want to show where it came from. And ultimately what these look like is these are just a sphere of electrons, just the noble gases that we have. So now I have this sphere, which is a positively charged sodium and a negatively charged chlorine. And these two are attracted to one another because they're opposite charges. And so they're going to make a compound of sodium plus combined together with a sphere of chlorine minus. And they're just going to start piling up, and you're going to get ultimately an ionic compound like we have here. Right, so it just continues to grow. And in fact, if you look at salt, sodium chloride, you're going to see that it's in this cube shape at the macro level. You can see them with a, with your naked eye. You can see that they're cubic because they like to form these perfect little blocks, right? Every single positive charge is surrounded by a bunch of negative charges. Every single negative charge is surrounded by a bunch of positive charges, and so on and so forth. The net charge, ultimately, the overall charge of this is equal to 0, right? This is +1 plus a -1 overall is equal to 0. Compounds will always be neutral. So these things will always be neutral when we're done. In fact, nothing can exist as a solid and have a charge. Everything has to be neutral. Okay, so that's how we form ionic compounds. We are going to talk about molecular compounds next chapter, but I do want to point out that here we have a molecule forming. So up here, ionic compounds, the really important takeaways, ionic, you're going to see the transfer of electrons, because metals want to give up their electrons and nonmetals want to gain electrons. An ionic compound is always going to be between a metal and a nonmetal. In fact, if you see a metal, you know you have to think this is an ionic compound. Okay, and then finally, they're always going to be neutral. Okay, so we're going to add enough positive and enough negative to make sure that things are neutral. A molecular compound, and I'm going to call this covalent, not going to quite work like that. What we're going to notice is a covalent compound is going to work by sharing of electrons. It's going to be nonmetal and another nonmetal, or a bunch of nonmetals. They both want to get rid of their electron, or they both want to gain electrons. So instead of getting rid of them, or instead of gaining them, they're going to share them. Okay, so if I have a hydrogen, well, I guess I should do chlorine actually. So if I have a chlorine like above, and it wants to bond with another chlorine, because they both want those electrons between the two of them, they're going to settle for just simply sharing those electrons. So that is ultimately how a molecular compound is going to work. Again, a molecular compound is just all nonmetals, and that's ultimately what you're going to get. These should be neutral as well, but there are times where it can be charged, and we'll talk about that. But it's the sharing of electrons. These are shared. That's a bond. This is there are 2 electrons here. It's shared between the 2. But we're going to focus on ionic compounds today. Okay, so with that said, we're going to start 5.2. Next, we're going to talk about how we actually form these compounds from the ions that we were able to determine.